we begin talking about linear transformations. This is an example of something that happens throughout mathematics, which is that we move from talking about mathematical objects to talking about relationships between them or maps between them. That starts even when you're in grade school and you learn to count objects like apples or cars or something. And then after a while, you develop the notion of like 3 or 5, which is kind of an isomorphism class of which you construct by doing a bijection. Right? You're matching up one car and one apple until you get the same number. And eventually you start to think of this sort of class of maps, or 3, as something in itself. And that process continues with layers and layer after layer of structure. So this class is no different, where vector spaces where our objects and vectors within them, but they're not really that useful by themselves. What's useful is to think about the right notion of maps between them and use that to relate them. And that's what the rest of the focus of the class will be. So in some sense, the class, in earnest, linear algebra is the study of these things, linear transformations, more so than the study of these. And we sort of begin now. So the reading for this, of course, is chapter 3. And the first thing I want to do is kind of an aside that relates to some of the things that you saw in the homework, which is to talk about, this is a category that we're studying, setting of vector spaces and linear transformations, and there's another related category of finite sets and relations. You had a homework problem where you had to look at relations. And this setting provides kind of a nice simplified model that we can use later on to understand vector spaces and linear transformations, just like we had this model of the dimension property relating to an area property or relating to counting points, right? So this aside that I'm talking about first today, the aim of that is to give us a similar intuition, and it'll become more literally true, the relation, as we add some additional structure to this. Okay, so this begins with finite sets. Finite set is just, a list of things there are finite many of. I'm going to give them numbers and letters to distinguish so that it's easy to talk about sets like A, which has elements A1, A2, and A3, and B, which has, say, 4 elements, B1, B2, B3, and B4. So a relation, if you recall, on these sets, A and B, you can think about it as somehow connecting A and B, is just a subset of the Cartesian product. So R, a relation, is just a subset of A cross B. And what's the set of all relations between A and B? Well, first of all, let's take an example. So what's an example? So A cross B as a Cartesian product is just a set of all pairs. One thing from A, one thing from B, so it's A1, B1, A1, B2, A1, B3, A1, B4, A2, B1, A2, B2. So it's the set of all pairs. There's 12 such pairs, 3 times 4 in this example. And a relation is just a subset of that, right? So e.g., A1, B2, A3, B1. That would be a relation. Here's another relation. Here's another relation. It's R1, R2, R3. So each relation is itself a set, and the set of all relations is a set. How would you describe the set of all relations between A and B? Well, it's something sometimes called the power set, right? It's the set of all subsets. If a relation is the same as a subset, the set of all relations is a set, which is the set of all subsets of A and B. So I'm just written 2 to the A cross B. And this notation is related to the homework, right? You remember you had a problem where you asked to specify a relation. All I have to do is look at these 12 possible elements and say, is each pair in or out? Assign it like a 0 or a 1. And that's what this notation comes from. It's like 2, 0, or 1. And for every element of A and B, I assign something. So it turns out that relations, like I said, you could think about relations as flowing from one set to another, like somehow connecting set A and B. So R could be a relation that I'm just going to draw sort of a little diagram here. I have a set A and a set B, and R somehow connects them. And if I have another relation S, which connects a set B, the same set B, to a third set C, as this diagram suggests, there's a way to combine these two, a way to plug R and S together or compose the relations. And this will turn out to be related to the way we compose linear maps once we've defined linear maps. So the rule is that the composition of S and R, so in this picture, this would be first R is a relation that connects A and B, and S is a relation that connects B and C. I can compose them to get a new relation. That new relation has to be a subset of A cross C, the Cartesian product of A. So this is going to have to be some subset of A cross C. I'm going to give the definition of that right now. And that's just pairs that agree in the middle. More precisely, the composition of S and R is the set of all pairs AC such that AB is a pair in R and BC is a pair in S for some intermediate thing B in the middle. So let's give a concrete example. Let's let A be A1, A2. Let B be B1, B2, B3, and C, C1, C2. And now I need to give you two relations. So how about R can be a relation with three elements, A1, B1, A1, B3, and A2, B2. And S can be a relation B1, C1, B2, C2. And we want to compose those two relations according to that rule. That is, we want to look at all the possible intermediate steps B and include pairs that have an intermediate that matches. So it might be best to write that as first as like a picture. So A has two elements, A1 and A2. B has three elements, B1, B2, and B3. And C has two elements, C1 and C2. And I can diagram the relation R as connecting A1 and B1, connecting A1 and B3, and connecting A2 and B2. That's R. There's A, B, and C. And I can diagram the relation S as connecting B1 and C1, and it connects B2 and C2. And the composition is just the relation, all pairs such that I have a path from the element of A to the element of C. So one of them is through some intermediate B. So this is one of the pairs, A1, C1. A2, C2 is another pair. This is a dead end because there's nothing connected to it. But if, for example, I put that edge in, then that would add another relation to S, and then there would be another pair in the composition. So S composed with R is just A1C1 and A2C2. So in your homework, you characterized a relation across as a subset of a Cartesian product like A and B. This thing has 6 elements. We found that there were 6 possible pairs, and I had to specify 6 numbers to be 0 or 1 to say which thing was in the relation and which was not in the relation. Now I want to think about those numbers 0 and 1 also as false and true. And form from that something called the Boolean semi-ring. So you're used to rings like the integers. In the integers, if I have 2 integers, I can add them, and I can multiply them. There's a ring because in the integers, every a has a negative a, such that the sum of those 2 things is 0. There are other things like the natural numbers, which are not rings but semi-rings. That is, they're still an addition and they're still a multiplication, and they follow the rules you would expect. But there's no additive inverse, right? 2 is a natural number, but negative 2 is not. So that's a semi-ring, an example of a semi-ring. And there's a semi-ring that's built out of false, true, and an or, called the Boolean semi-ring. I'll write B for it. And in the Boolean semi-ring, instead of addition, we do or. And instead of multiplication, we do and. And with those 2 rules, I can write formulas in this Boolean semi-ring or variables in it, and they do just what you'd expect. So one of the other properties a ring has is that it distributes. Right? Multiplication distributes over addition. That's true in the Boolean semi-ring. That is, we want something like, suppose, x, y, and z are true or false. And I have this Boolean semi-ring. I could write this one of 2 ways, x times y plus z. This would be the distributive rule, equals xy plus xz. Or writing it with the and or notation, I'm saying x and y or z equals x and y, or x and z. If you think about it for a little bit, you can see that that's true, right? So and distributes over or for Boolean expressions. So for a concrete example, true and true or false, plugging in true for x, true for y, and false for z. That's going to be, well, true or false is true. True and true is true, so that's true. And that's equal to the distributed version, true and true, or true and false. Right, that's false, but then I have an or. Okay. And you could check all the other truth tables to prove that this was distributive and, in fact, a semi-ring. Okay, so now I want to think about a relation as for every pair, instead of giving you a 0, 1, I give you, a false or a true, or I give you a 0, 1, and I think about it in this Boolean semi-ring. And we have this composition rule for relations. And the point is that you can express this composition rule in terms of arithmetic in this semi-ring. So let me explain how that works. So I'm erasing this rule for composition, but we're going to put up an equivalent rule in a second. So a relation is a subset of a relation from A to B, R relating A and B is a subset of A cross B. And I can think about it, the point of this, or part of the point of this discussion, is that I can think about it as a function, as in your homework, which eats an element of A cross B and spits out a true or false value, right? if a pair is in the relation, it says true. If a pair is not in the relation, it says false. Just another way of describing the relation as a function from A cross B to the Boolean semi-ring. Then I have a composition rule. So if R goes from A to B and S goes from B to C, question? So in other words, R is a function from an S goes from B cross C to this true or false Boolean semi-ring. I can define the composition S composed with R applied to a pair. So S composed with R is going to be a subset of A cross C, or equivalently, S composed with R is going to be a function from A cross C to the Boolean semi-ring. For every pair of an element 1 in A and 1 in C, I assign a true or false. So I just tell you what it does to each pair to define it. And let's define it this way. It's the sum over all the intermediate elements of R applied to the pair AB. So this is a true or false value, depending on whether the pair AB is in R or not, times S applied to the pair BC. So that's a true or false value. It's true if BC is in S, and it's false if it's not. And in here, the addition and the multiplication are happening in this Boolean semi-ring. So in other words, this is just a notation for I'm taking the OR. So I check for every intermediate thing. If any of those, for any of those, it's true that AB is in R and BC is in S, then I put AC in the composition. That's the same rule as the rule we had up again a moment ago for composition, right? Same composition rule. That is, that's equal to, this thing is equal to pairs A comma C such that AB is in R and BC is in S for sum B in B. The for sum is what becomes the OR, and this is the AND. Okay. So the point is that this is, we haven't written down matrices yet, but when we do, that's the same rule as the composition for matrices. This is the same rule. It's just that instead of being a matrix, instead of being a function from A cross B to the Boolean semi-ring, we just replace this with a field. Then the addition becomes addition in the field. The multiplication becomes multiplication in the field. And we get matrices over that field. Or you could even put in something else there, like the integers, and it would still make sense. Okay. So because they have essentially the same composition rule, except that we've just changed what goes here, that's sort of the reason why there will end up being lots of properties in common between this category of sets and relations and the category of finite dimensional vector spaces and linear transformations. Okay, so as an aside, just building some analogies that will grow when we start talking about bases. But now let's get into talking about linear transformations proper. So as we said, we want to move from studying the objects to studying maps between the objects. And those maps should be structure preserving. So whatever structure we have on the objects, set structure, then we had additive abelian group structure, and then we had a action by the field, scalar multiplication. We want to preserve that structure as much as possible to figure out the right notion of maps. Trying to figure out some axioms, and so for the vector spaces, the bottom layer structure of the vector spaces was the vector spaces were sets. And so, when we're thinking about what a map between them is, it makes perfect sense to say something like, well, the map between them is going to be a set function which satisfies certain axioms. That wasn't true over here, right? Relations are not necessarily functions, so they'll end up sharing properties, but these are going to be honest functions, valid on every point of V, and assigning one value of W for every point of V. So we're first going to say it's a set function with domain V and codomain W, both of these vector spaces. We can say that because vector spaces are, first of all, sets. And of course, these things are going to be able to be composed, just like functions can be composed if the domains and the codomains match up. So we summarized our structure for a vector space as being an additive abelian group with a field action or with a scalar multiplication. And those are the two things, at a minimum that we want to preserve, right? So we know that if we have two vectors, we can add them. And if I have a field element and a vector, we can scalar multiply. And we'd like our functions, our set functions from the set of vectors in V to the set of vectors in W to preserve those properties. And that's our definition. So let V and W be vector spaces over same field F. A function F from V to W, just a set function at this point, is a linear transformation from V to W if for all uv in V and for all a in F, we have two things true. F of u plus V is equal to F of u plus F of V. So this is saying that F is a group homomorphism, or at least part of that. Homomorphism, if you remember from 311 or some other class. So it's saying that there's this additive abelian group structure in the vector space, and addition, if I add first in V and then apply F, it's the same as if I apply F to each and then add in W. The addition here is in V and the addition here is in W. So it's a group homomorphism. And I'm not requiring that it gives me the same answer if I switch the order of the vectors, because you can get that from the fact that this has to be the same whether I flip them or not. Right? This is an abelian group and this is an abelian group, V and W. And in your book, this is called additivity. So the second property, B, is that it respects the scalar multiplication. That is, if I do my scalar multiplication in V and then apply F, I get the same answer as if I do my scalar multiplication in W after applying F. And so this is that it respects the scalar multiplication, or that it's a homomorphism of these things which are abelian groups with the field action, vector space homomorphism. And in your book, it's called homogeneity. It's homogeneity of degree. So sometimes people talk about, if f of lambda v equals lambda to the a, f of v, they would say that's a function which is homogeneous of degree a. So we're talking about homogeneous of degree 1. Can pull the scalar multiple through. Doing that on either side is perfectly valid. OK, so this is a very, we had a lot of properties of vector spaces, and we've only talked about two sorts of preservations that happen here. And the point is that from these two assumptions, you can conclude that all the other properties that you'd like are preserved. So if I have a group homomorphism, there's something often else, some other axioms which are required of that, such as associativity, or the fact that it sends the identity to the identity. So we should check that we've assumed enough so that, for example, the identity gets sent to the identity. Inverses get respected and all that kind of thing, right? Let's make some observations. First of all, claim that if I take a 0 vector in V and I apply F to it, I get a 0 vector in W. And you can prove that just given these properties by doing something like f of the 0 vector in V is equal to f of, for any vector in V, V minus V, because that's equal to 0. And that's equal to f of V plus f of minus V by property A. By property B, I can pull the scalar multiplier minus 1 that's lurking here out to get f of V minus f of V. And then by additive inverse axiom in W, this is going to have to be equal to 0 in W. Another observation is that we can rephrase or combine A and B in various ways, some of which are more convenient than others, depending on what it is you're trying to prove. So f is a linear transformation if and only if, well, it satisfies that definition, but only also I could use the definition f of A u plus bv equals A f of u plus b f of v. And that's for all A, B in the field and for all u, v in the vector space V. So that's combining the scalar multiplication and the addition axioms, homogeneity and additivity. And in fact, you can prove, and I think it may be an exercise that I'll ask you to do to prove that you can get rid of one of these scalar multiples and it'll still be enough. So that's also true if and only if f of A times u plus v equals A f of u plus f of v. And again, that's quantified for all uv and v and for all A in the field. And I can go in the other direction to make it more complicated and say something like for all AI in the field, VI in the vector space, a collection of these things, I equals 1 up to n, and require that f of any finite sum from I equals 1 up to n, AI, VI, I can push f through the sum. And depending on what you're trying to prove, one of these might be more easy to work with than others. For example, if you're just trying to check that f is linear transformation, this is somehow the fewest things to check or the fewest operations. If you're working with a linear combination, you'll want to use this property or this version of this definition. Right? Because you already have a linear combination, you just want to push it through the linear combination. Let me pause for a moment and see if you have any questions about what I've said so far. We're about to go up sort of another level. Make another jump of abstraction. Let me show you with me before I go. So we said that, well, we said that the set of all relations from A to B, or connecting two sets, finite sets A to B, was itself a set. Right? That's kind of not surprising. It's this power set. Similarly, the set of all linear transformations from a vector space to another can be made into a vector space. It's itself a vector space. set of all linear transformations from one vector space to another is again a vector space. Now remember that during the first week or so, one of the examples of a vector space we talked about was functions from, say, 0, 1 to R. And another example was some field to some power, lists of elements in a field. And in order to define things like addition and scalar multiplication in these, addition and scalar multiplication in terms of addition and ordinary multiplication in R or F. Right? If we wanted to add two functions, we just added them pointwise using the fact that we know how to add in R. If we wanted to multiply two functions, we just multiplied a scalar times a function. We multiplied pointwise, the scalar times the value of the function at any particular point. That was the definition we made, right? We sort of induced the addition and scalar multiplication structure here from what we knew about how to do operations here. So we're going to do the same thing with this, right? So I have a function, linear transformation from V to W. W is a vector space. I have another function, V to W, which is a linear transformation. And W is a vector space. And we're going to define addition of these two things, F plus G, in terms of addition and scalar multiplication in W. So we want to define F plus G. F and G are linear maps from V to W. That's the notation that's in your book. There's other notations that we'll talk about as well for the space of linear maps. F and G are linear maps from V to W, and so we want F plus G to also be a linear map from V to W. In particular, it's a function. To define a function, I can tell you just what it does to every element of its input. So to define F plus G, so this is addition. This is the definition of addition in the new vector space of linear transformations from V to W. We're defining something. F plus G with a plus happening in this vector space. I define it by saying what it does to a vector V, which has to be in the vector space V. And by what we just set that equal to, well, F of V plus G of V. And this addition happens in which vector space? So F goes from V to W. So F of V is an element of W, right? So this addition is happening in the W vector space. So from the addition in the W vector space, we've learned how to add linear transformations. Same thing for scalar multiplication. We want to define scalar multiplication. AF for A in the field. This is going to be a new map, so a new element of the space of linear transformations from V to W. And we're going to define it in terms of what it does to an input vector V, which is in V, by using the fact that we have a scalar multiplication already in W. So this here is scalar multiplication in W. And this is function application. It's happening here. And the function application over here is happening there. So I want to mention one notation, which is that if I have a vector space V, which is over a field F, this field is also a vector space, one-dimensional vector space over itself. And so I can construct the space of linear transformations from the vector space V to its field. This space has a special name, V star. V star or V dual. You could think of this as linear functions from the vector space down to the field. If you have an inner product, this is often given by the inner product, right? So you have a vector sitting in space. You could take the dot product of that vector with any other vector, and that defines a function. So that vector you started with is an element of the dual, thought of that way. And we'll see lots more of this later on. OK, so we have an addition. So we have a set of functions from V to W, which are linear. And we have an addition. And we have a scalar multiplication. Is it a vector space? Well, in your homework, you'll prove that it's a vector space. In the next homework. So one of the other key elements of a vector space that you'll need in order to do that homework is an additive identity. So what's the additive identity here? So we need some special function, it's called z, from V to W. Another good notation for it, since it's going to be an additive identity, it's going to be the zero vector. Right? It's going to be the zero vector in the space of linear transformations. So it's going to be a linear transformation thought of as a vector in the vector space of linear transformations. Its name is going to be 0, like the 0 and everything else. So it's yet another thing, which is a 0. What function should that be? So we know from addition, right, we know what property we want it to satisfy, right? We want f plus z of v equals f of v plus z of v. And we want it to be that to be equal to f of v, right? Because then adding this thing is the same as the identity. It gives me back what I started with. Right? So what should this function z be? If I give you a vector, what should z do to that vector? Take it to 0. It's a constant function. Sends every vector in V to 0. It's a very boring function. Then this will be true, because this will always be 0 in W. This was addition in W. F of V plus 0 is equal to F of V, additive identity axiom. But we have one more thing to check. What's that? We just defined it to be a function, right? But we're not allowed to use any function. It has to be a linear transformation. So we have to check that this function we just defined, 0 LVW, is in fact in LVW, i.e. that it's linear. So this is truly weird. So we want to show that z applied to u plus v, or let's say cu plus v, so c is a field element. We want to show that that is equal to c times z of u plus z of v. Right? That's what we need to show that it's linear. Well, OK. This is equal to 0 by definition. By definition, this is equal to 0, c times 0, which is equal to 0. And this is equal to 0. So 0 equals 0 plus 0. So it's OK. So it's linear, but sort of nothing happened, kind of. Right? Linear in a very trivial way. But we had to check that in order to show that this really was going to play the role of the 0 vector, because otherwise it wouldn't even be in the set that we were considering. So I want to mention at this point some names for this thing. So the name that appears in the book for the set, the vector space of linear transformations from V to W is L, script L of V to W. Another name you might see is something like HOM VW, which stands for homomorphism, or morphism, even, from V to W. And in this notation, it's kind of assumed that this means basically structure-preserving map from this space to that space. And it's assumed that you know what structure you're talking about. So to be more precise, we should say down here, homomorphism of F vector spaces, or morphism of F vector spaces from V to W. And if you remember this piece of notation, the special name for the dual space, there's another thing we'll see more of later, which is this. Space of linear maps from V to W is the tensor product of two vector spaces, V dual and W. You think about this as a little bit like if we were in bases, this would be like saying every linear map is given by a matrix. This would be more like a matrix here. Kind of like column and rows and all possible ways to fill it in. But we'll see more of that. For now, you could even just take this to be a definition. Since this is defined, and this is defined, and that's defined, this could be, you could take this to be the definition of what this symbol means, tensor product, V star tensor W. So the last thing I want to mention is that there's more special maps in if we're in another special case. So suppose I take the set of maps from V to itself. This, by the way, has another special name, endomorphisms of V, morphisms from V to itself. Maps from V to V. So we remember we can compose functions and we can compose linear transformations so long as their domains and codomains match up, right? So if we were in the case of here where I have vector space, say, U, V, and W, as long as F goes from U to V and G goes from U to W, then G composed with F makes perfect sense. And it goes from U to W. If I have two functions, F and G, inside of LVV, so functions from V to itself, then those can always be composed in either order. So in this one, I can't compose. The other thing wouldn't make sense, right? F composed with G makes no sense because they don't match up in the middle. Here, I can go either F composed with G or G composed with F, and either of those makes sense. It's fine. There's a special function in here besides 0, which has the property that there exists a special map, I to V, which is a linear transformation from V to V. And it has the property that F composed with I to V, which always makes sense, so such that for all F in linear maps from V to V, F composed with I to V equals F equals I to V composed with F. Right? There's some special linear map, which I'm calling I to V, which is an element of this that has this property. So what map is that as a function? The name is a hint. So what is I to V of V? V is a vector in the vector space that we're talking about. I can define a function by telling you where it sends v. Where should it send v for this to hold? Not the inverse function. Not every function, for example, 0 doesn't have an inverse. So not every function has an inverse. You have an idea? Well, sometimes people denote it as 1. But it doesn't send everything to 1 either. It's v. It's the identity function. The map which sends everything just to itself. And then you have to prove that that's linear, but that's pretty easy to do. Okay. So this is the identity. It's a new special map. It doesn't make sense to talk about that in this case, because there's no self to send it to, but as soon as these are the same vector space, it does make sense. That's a special map. You know, if it were in a matrix land, this is the identity matrix. Represents that transformation. Whereas the 0 is represented by the 0 matrix with all zeros. Okay. Well, I'll see you on Wednesday.